Hello and welcome to this presentation. We are going to be talking about phase engineering on the halide perovskites. We got our research concept from this academic, Professor Amita. And just a brief introduction into all this. What is phase engineering? Well, phase engineering just describes a subset of nanomaterial engineering, which is the manipulation and synthesis of materials in the nanoscale, anything between 1 to 100 nanometers. Phase just refers to the atomic arrangement of materials. And from this diagram, we can see that some nanomaterials have some unconventional phases. And through phase engineering, we have been able to do phase transformations, which make them more applicable in the real world. Perovskite is just a general name for a series of compounds with a chemical structure of ABX3. We'll be looking at that in more detail in the following slides. Why is this all important in the first place? Well, engineering on the nanoscale is heavily driven by modern problems and needs, and we can offer solutions through renewable energy. Looking at the structure of perovskites, we can see that AB cations can coordinate with 12 and 6 anions from different structures to form alternate crystal phases, which is where phase engineering plays a part in the first place. On this diagram on the right here, we can see the bond and stick model of perovskites, and the X just refers to either halide or an oxide, and we will be focusing on the halide perovskites due to their unique qualities that give them promising applications to the real world, such as semiconducting ability, which is brought about through overlapping of p orbitals in the x side anion and the b side cation. And phase engineering plays a part here as it acts as a mechanism to enhance its properties. And one of the main methods is surface modification, where ligands are bonded to the surface of the perovskites. And this is very important because when particles are very small, surface energy is dominant factor that decides which crystal phase is more favorable and stable. As we can see, an example on the right here, image D is a non-stable phase, image D is a stable phase, and this change is brought about through ligand addition. How is this linked to one of the global challenges? Well, it helps combat the climate crisis. Obviously, the climate has become one of the more central focuses for scientists all around the world, and renewable energy has been at the forefront of this environmental battle. Halide perovskites play a part because they make up solar cells, which are the building blocks of solar panels. And through this graph here, we can see that since the beginning of the 21st century, the cumulative installed solar PV capacity worldwide has risen in exponential fashion. This is due to the breakthroughs in phase engineering. Solar cells have become more efficient. Um, this means it's playing an active role in combating the climate change. And in 2022, PV capacity was at a bit more than a gigawatt, making it a record year for installations. This is just a statistic here to show that it's becoming more recognized around the world. And just to conclude, the modern world faces a huge climate crisis, and chemical engineers are helping this issue by offering solutions in the field of renewable energy. And one of the more prominent aspects is solar panels, and phase engineering of halide perovskites allow for the making of this. And this is just my references page. Thank you for listening.